Hello and welcome to a new video lecture. In this video I shall review a method for anomaly detection based on tensor decomposition and genetic algorithms. This paper is co-authored by Deng et al. In this paper, the authors propose two novel algorithms. The first is a novelty detection support tensor machine based on Tensor Decomposition. Novelty detection is simply classifying a sample as a regular data point or anomaly. To explain what an anomaly means, let's take a very simple example of a classroom, where most of the students are between 10 to 15 years old, but a few students are below 5 years old, and in this case they are called a genius, but still they are anomalies or outliers, since they break the norm. The same goes for older students. The authors propose a second algorithm that uses a genetic algorithm to iteratively reduce the subset of features which is used for model training, and in parallel optimize the algorithm parameters. One class support tensor machines extend the idea of support vector machines, where the algorithm is trying to find a hyperplane that acts as a decision boundary to best separate the data points into regular and irregular samples. The hyperplane is defined by a tensor W and an intercept vector P. I do explain the optimization algorithm for support vector machines on a YouTube video, which you can find attached in the lecture material. Now let's talk about the genetic algorithm. The genetic algorithm they have proposed is as usual initiated with random binary values in chromosomes. The chromosomes consist of P of C for model parameters and N feature subsets for each unitary matrix. Thus, it represents an encoding of both the hyperparameters to train the model and the feature selection algorithm. Next, they define the objective function that does two jobs at the same time. First, minimize the number of features that is used for dimensionality reduction. Simultaneously, maximize the outlier detection accuracy. In genetic algorithms, it is very common to find fitness functions with multiple objectives. As an example, you might want to get the cheapest possible air ticket, and at the same time you want to get the fastest one without any transit. That's multiple objectives. You are minimizing the price, maximizing the speed, and so on. Now we have got the architecture of the algorithm. The algorithm begins at the top right corner of the screen by loading high-dimensional data in tensor space and splitting it into training and testing datasets. The initial random values for features and model parameters are decoded from the genetic algorithm part. Then the one class support attacker machine classifier is trained. The fitness function is evaluated, and if the number of generations has not exceeded the maximum evolution generation, then the genetic selection is performed using roulette wheel selection, and the best fit chromosomes are selected for crossover to generate a new generation. That is, they are selected for mating together to produce offsprings. The process repeats, and once the genetic algorithm has terminated, its accuracy is reported on the testing set. That is, we use the testing set only to evaluate the overall accuracy of the model. The authors test different vector-based and tensor-based outlier detection methods on 5 datasets. The datasets are similar to Montes sensor dataset, which is a collection of sensor readings that is located in different geospatial locations and reports values at constant time steps. That's why the dataset is represented as a 3-dimensional tensor having time, location, and type as axes. In this table we can see the dimensionality of the 5 datasets, which are used for testing the proposed algorithms. You can see that they are all 3-dimensional tensors, and if you look at the last one on the very right of the screen, which is named USFG64, you can see that it has the highest dimensions of all, 64 by 40 by 20, which is a high dimensional tensor. The second row represents the number of samples taken for performing these experiments. In this case, it doesn't exceed the value 1200. The authors of this paper have conducted many accuracy tests, and then for each algorithm and each number of training iterations, they have reported the average and the standard deviation for the obtained accuracy, that is outlier detection accuracy. We can observe that the accuracy increases from the top to the bottom, proportional to the number of training iterations as it increases. We can also observe that the accuracy increases from the left to the right. That is, on the left columns we have got vector-based methods, and as we proceed to the right of the table we have got the columns for the tensor decomposition-based methods. We can see that the accuracy for tensor methods are much higher than that for vector methods. That's because tensor methods preserve both tempospatial correlation and hence perform better classification. The best results are obtained using genetic algorithms to drive the training of the classifier. The reason why I'm more interested in this paper is because they have conducted many experiments to test the novel methods proposed. First, they have injected 5% of artificial anomalies drawn from a uniform distribution into the dataset and reported the effect on the overall accuracy. Then they have shuffled the data along the tensor dimensions and observed the results. Again, they have tried different values for the core tensor dimensions in case of Tucker decomposition. That's why we can note here that there are only two methods that were applicable for this test. Those are the methods that use Tucker decomposition. Both of them actually were proposed in this paper. Next, they have studied the effect of the number of features on the overall accuracy. And they found that as the number of features increased, the accuracy has dropped. But again, genetic algorithm-based one-class support Tucker machines performed best. Finally, they have studied the effect of the train-test split fraction. As you add more data to the training, the higher the accuracy you get. I hope this was inspiring for you to approach IoT and embedded systems from an artificial intelligence perspective. Thank you and see you in the next lecture.